Well, thank you, Steve, for the introduction. I just want to mention that this work is the result of a collaboration with Guillaume Urvoy-Keller from the University of Nice and Biersack, who used to be in Eurecom. And before starting, I just want to remind you where BGP is into the grand scheme of the internet things. So the internet, as we all know, is a network of networks, and all of these networks are referred to as autonomous systems, or ASs. And they use the Border Gateway Protocol to exchange routing information between them. And the particular phenomenon that we're going to be interested in today is the forwarding to the most specific route that exists. So in this example, if we have AS1 that announces a fairly large 1/8 prefix, and concurrently AS2 that announces a 1.255/16 prefix, all traffic to any IP address within 1.255 will be forwarded automatically to AS2 instead of AS1. So in general, our research goal is to detect prefix hijacking, and we know that these more specific prefixes are used by ISPs to do things like traffic engineering, for example, to make sure that traffic is coming through a certain upstream or a certain part of the network. But there have also been a number of cases, public cases, where this propagation led to large-scale denial of services. The speaker before me talked about the YouTube hijack. This was a case. And more recently, there was a spam house was hijacked by spammers who were unhappy to be detected and blacklisted. So for this reason, we thought it would be quite useful to describe and to understand the use of overlapping prefixes in the global routing table. Now, how should we go about and do this? So another hypothetical case, we have three prefixes, a /8, a /16, and a /24. And the intuitive way to compare them would be to make three pairs of prefixes and to compare them 2 by 2. But let's imagine that the /8 belongs to a tier 1 ISP, the /16 to a tier 3 ISP, and the /24 to any business or corporation. When the corporation wants to get IP addresses, what they will do is go to their local ISP that provides internet services, and this ISP will assign them a chunk of their own IP space. So in this case, it is very likely that A, who gave the IP space to B, doesn't know about C. So comparing the /24 with the /8 will not produce any meaningful results, because these guys did not decide that this network should exist. If we take the same situation, but in this case the /8 belongs to a private corporation, then it is these guys who decided to create first the /16, but also the /24. So the comparison between the /16 and the /24 doesn't make much sense. They should be compared to the base prefix, which is the /8. So depending on the allocation of these prefixes, you can see that some comparisons should or should not be done. So now, just a few words about the data sets. In order to find out who own these prefixes, we're going to use the Internet Routing Registries, and in particular the INetNum objects, which detail IPv4 allocation. We've been able to secure access to the 5 existing versions of these databases, which are distributed, and we extract in August 2014 about 8,300,000 registered prefixes. At the same time, we take the BGP data from RIPE. In particular, we take the Amsterdam collector, which has over 40 geographically diversified peers, also in August. And we extract about 630,000 prefixes. So again, in one case, IRR, we had, this graph exactly, we had 8 million, and the other case we had 600,000. And if we compare, we see that for the prefixes that are larger or equal to /24, so the left-hand part of the graph here, the distribution almost matches in both data sets. However, for very specific, very small prefixes, we see that there is up to 1,000 times difference of entries. And we explain this by the fact that a good practice in BGP is to not propagate routes that are longer than /24, meaning that we will not see them from the collectors. Also, when we checked these entries out, we found that a lot of them are not necessarily for people that actively use BGP, but are there to provide contact information for the people that use this IP space. For example, the /32 prefixes, which is another way of saying that these are IP addresses, are single servers that have been rented by people from diverse providers. So earlier I said that we're going to group the prefixes in order to compare them in a coherent way, and basically this is why we introduced the concept of families of prefixes. So a family of prefixes will contain only prefixes that can be compared together, and we have three kinds of prefixes in a family. We have the father prefix, and we have children prefix, and then we have subfamily prefixes. The father prefix is always the registered prefix, meaning that we have 8 million distinct families, all of which have been registered as is indicated by the little book icon here on every family father. And then when we have these families, we populate them with the BGP data. And a BGP prefix is either exactly the same as the registered prefix, or it is more specific than this prefix. So for this reason, if it's the same, of course we don't need to do anything, but if it's more specific, we need to add it to the family. And in this case, we call these the children prefixes, and we add them to the family. For example, here, the AB/18s are part of family 1 because they're more specific than the /16, but they're only found in BGP as indicated by the router icon, so they're not family fathers. And as you can see here, some families belong to other families because they're parts of a number of assignments on different levels, and this leads to the concept of subfamilies. So family 1 has a subfamily, which is family 2, and family 2 has two subfamilies, which is family 4. So once we know this, we can compare and see how prefixes behave within a family. And the first thing that we did is to look at the distribution of children prefixes. So these are the prefixes that we find only in BGP and not in the internet routing registries. And here we plot for every combination of family father mask length and child mask length, the histogram of the distribution. So for example, here, if we take a family of a /16, we see that the bulk of the distribution is for children of a mask of /24. And actually, as you can see, this observation holds true for every mask length. And we can explain this again by the fact that we don't see anything more specific than /24 in BGP anyway. But also we can explain it by the fact that due to the scarcity of IPv4 address space, a lot of people prefer to assign smaller networks, in this case /24, that will have a high utilization rate, than a larger /16 that will have a very few machines in. We do the same plot for subfamilies, in other words, for external assignments from to other corporations, and we see that here the bulk of the distribution is for /29 prefixes. And if you think about it, a /29 is only 6 usable IP addresses, which is not a lot, but is enough for small to medium corporations to hold their internet business. And it's actually, this is, we think, a result of the fact that there are a lot more tier 3 ISPs than any other ISPs, and these ISPs provide connectivity to the edge of the network. So we have a lot of entries at the edge of the network, which could result in this natural predominance of /29 assignments. All right, so now let's look at how many children we have per family. And here we see that for 25% of cases, we don't have any children. And sorry, only for 25% of cases we have children, so for 75% of cases, we don't have any child. And we can say something similar for subfamilies. We see that only 17% of them have subfamilies. So the most people do not announce different prefixes, and they do not give out any further IP space. And these are the numbers You can see that in 73% of cases, this is just simple, which means that for most cases, people do not divide their space anymore and do not announce any extra space or subnets into BGP. So we tried to see if there's any correlation between all these configurations, but we couldn't find any. Meaning that children and subfamilies cannot be correlated. What's more interesting is we looked at how many times the same IP space is announced within a family. So basically for this, we count the number of IP addresses that are within each prefix and we compute the ratio. For subfamilies, we have this plot, meaning that for 80% of cases, there is no overlap, but this can be explained from the fact that most families don't have any subfamilies. More interestingly, children prefixes, so BGP over announcement in, 35% of cases, overlap completely the registered prefix, meaning that the registered prefix, if it is announced, is never used to route traffic. And even more interestingly, when we compute the sum of these two ratios, it goes over 1. And to illustrate, we have this real-world case where the registered prefix is a /19. It is announced in BGP as a /19, and then these guys go and announce the two covering /20s, and then they registered the /21s, and they also announced them. So basically, this IP space is announced 4 times concurrently and not in a transient manner in the BGP routing table. All right, so these are not numbers, and what can we do with this now? Basically, we took a number of companies, I'm sure you know most names, and we classified them into tier 1, tier 3, and private corporation for lack of a better name. We looked up at the number of distinct families that they have, so the number of registrations, and then we added all their number of children, BGP announcements, and subfamilies suballocation. And what we see here in the ISP division is that they have a real large number of subfamilies, meaning that they actually spend a lot of time to put information into the internet routing registries. And comparatively, they have very few announcements that they do not declare from the administrative viewpoint. Private corporations, on the other hand, it's the total opposite. So we see that in most cases, there are next to absolutely nothing in terms of additional registration information, but there is a lot of prefixes in the BGP routing table. Apart from 2 cases, which is OVH, which is a host email provider, host provider, cloud provider, and so on. And Yandex used to be or still is the most popular search engine in Russia. So these 2 networks probably have an architecture that is close in size and complexity to those of ISPs. And the fact that corporations actually do not push this information into the public registry seems to suggest that they consider this as private corporate information and they don't want people to know about their internal organization of the network. Yeah, I just said this. All right, so in conclusion, 74% of families do not have any children, which means that for 74% of all cases, they just announce the prefix as was assigned by the ISPs, by the REERs, which is nice because this is what they should do. And this confirms previous experiments by Bu et al. In 2004 that was exploring the growth of the BGP routing table, and they said, okay, it is growing not because people are misbehaving, it is growing because there are more and more people connecting networks. I did not detail this result, but in the paper we show that 15% of families do not announce their prefix as assigned. So that means they receive a prefix, they do not announce it as is globally, they just announce a subpart of it, or they don't announce it at all. And there was a NDSS paper that showed that this kind of space could easily be hijacked and used for malicious intentions. Finally, I showed you through the use of real-world cases that using the BGP, the routing view, and also the administrative level view of the internet routing registries, we are able to uncover the kind of business and the kind of size of the network of a corporation. Still, I think the nicest outcome of this work is to show the value of the internet routing registries. So the IRRs have been quite debated in the BGP community, and sometimes in a very hard manner. We know for a long time that IRR is a good idea, and keeping them up to date is a good practice, and this actually dates back to before the internet days. In 2004, there was a study by Steganos et al. That said, okay, we're looking at this data, it is completely inconsistent, and the accuracy is not very good. And then still, 3 years later, they say, okay, if we take this information and we build a system that we use to validate incoming routing information and put it on top of BGP routers, we can improve significantly the resilience of BGP. More recently, Can said, okay, we compared the IRR with BGP, and we see that 78% of all ASs publish everything that they have about their network in there. And today I showed you that, yes, there's actually a lot of work by ISPs to push information and to keep it up to date. And this means that if they spend time on this, they find it useful and they find a use for it. So the information contained in the IRR cannot, in our opinion, be considered as entirely stale, inaccurate. So you should maybe take it with a grain of salt, but it provides a unique administrative level point of view into a network. And as some of you who may know my work before, we showed that it was quite useful in terms of trying to find prefix hijacking. So future work includes to try to study the AS level relationship between a family and its subfamilies to know how they are organized in terms of a AS graph. Also study the number of unannounced family, and by this I mean the very specific announcement. For example, we're intending to use a traceroute to see if they are located close to the bigger IP range that announces them. And we have successfully extended this work in order to validate sub-MOAS announcements. We have a paper coming up in the next JSAC, so it's the special issue on the troubleshooting and algorithmics of the internet. And if you're interested, you can look it up. It's quite good. And if you have any questions, I'm happy to answer.
Thank you very much.
Quentin, thank you for this really wonderful presentation. I was just wondering, did you correlate the data of overlapping prefixes maybe with IPv4 transfer data?
No, because first of all, I didn't think of it, and I don't have this data. So for the IRR, we have quite an extensive archive now, because we've been collecting them since 2012. Transfer data we don't have.
Well, maybe we can provide you with the transfer data.
Okay.
And I think it would be also interesting to see the development over time, right? We have the BGP data historically, so that should be no problem. And yeah, about the routing data, about the registration data, I think we're going to find a way to provide you with that data.
Okay, that would be.
Thank you.
Yeah, thank you.
A little anecdote today. I received mail from an address broker, like people who try to buy and sell IP addresses.
Yeah.
The company name is /19.com.
Okay.
So it reminded me, I was intrigued that you were finding so many /29s. They should be in the BGP table, right? Because of filtering.
Yeah.
Except maybe in our research networking world, where we internally we have some more specifics that are allowed. So did you find these /29s in the routing table, and did you look?
There are some of them. If we look at this plot, I don't know what it did with the pointer. Basically, the top red line, this one here is /29, and we see that there are Yeah, about 1,000 of them that are announced.
Okay, so
The thing is, they are announced. It's just that they are filtered before they reach the collection point that we use.
That might be actually worth doing active measurements to check,
Yep.
flag first those /29s and find out what's happening. Is there nothing? Is there a good reason? Or is it just researchers actually using this? Any other question? I've got one. You mentioned early on in your hypothesis that it's not really worth doing all comparisons between more specifics. I tend to disagree with that assumption in the sense that how much do you lose or what interesting stuff might you actually find out in how people actually use their address space or for what purposes, or in terms of more reverse engineering, what they really do rather than just flagging them as types of corporations that use address space in a rather binary manner.
Yes, okay. So if our goal in this work was really to classify and understand and clarify this use, okay, if you consider it in terms of security, so prefix hijacking, then okay, you must do more comparisons, of course. But it's also, if you see two networks originating from two different ASs and one of them is more specific and you know that there are two independently registered networks, it's also useless to say this is suspicious because it is not.
I wasn't mentioning security, but more trying to understand the internals of networks and find out, are they really doing traffic management, traffic engineering? It's like you've got OVH that is a data center-based network. Well, I expect to see clusters depending on the...
Actually, this is future work. When I said that we want to see a family and its families, this would be this case then, to compare the two families together and see how they behave.
Yeah, but I think it shouldn't be that much work then to look at the more specifics and then tag or find out classes or families that shed quite a lot of light on
it shouldn't be so much work. The hardest is to define actually a metric that is actually meaningful.
It's easy.
And honestly, so far I haven't found it. If you have an idea, I'm happy to take it.
As long as you do the work. Okay, let's thank the speaker again.
Thank you.